Chapter 14, Convergent Boundaries. Mountain building. Mountain building has occurred during recent geologic past. The American Cordillera, the Alpine Himalayan chain, mountainous terrains of the Western Pacific. So Earth's major mountain belts. So these reddish mountain belts, these are young mountains, typically very high and rugged. These purple mountain belts are older, more worn down mountain belts. Okay, for older Paleozoic age mountains, the Appalachians and the Urals in Russia. These mountains are deeply eroded and topographically less prominent. Orogenesis is a process that collectively produces a mountain belt. Here's Mount Kidd in Alberta, Canada. Okay, so geologic setting before faulting, it's really flat, and then with the faulting and stress and pressure, that's caused these folds here in Mount Kidd. Mountains that display faulting and folded rocks are compressional mountains. They display visual evidence of compressional forces. Plate tectonics provides a model for orogenesis. Earth's major mountains have formed along convergent plate boundaries. Major features of subduction zones. Okay, so convergence of subducting plates. So major features of subduction zones is volcanic arch, deep ocean trench, a forearch region, and a back arc region. Volcanic arcs. The subducting slab partially melts the overlaying mantle wedge. Melt migrates upward through the overlaying oceanic lithosphere and forms a growth called a volcanic island arc or an island arc. When the melt migrates through continental lithosphere, a continental volcanic arc is created. So here's our subducting oceanic plate. Partial melting, the melt migrates upward because of volcanic activity, is producing a volcanic island arc. Deep ocean trenches are created when oceanic lithosphere bends as it descends into the mantle. The trench depth is related to the age of the subducting lithosphere. All lithosphere is cold and dense. The plates subduct at a steep angle, producing a deep trench. Young lithosphere is warm and buoyant. The plates subduct at a shallower angle and produce shallower trenches, if any trench at all. Forearc and back arc regions. The forearc region is area between the trench and the volcanic arc. The back arc region is located on the side of the volcanic arc opposite the trench. Both regions consist of pyroclastic materials and eroded sediments. Tensional forces prevalent in these regions cause stretching. Extension and back arc spreading. When the subducting plate is cold, the plate sinks vertically as it descends along an angled path. This causes the trench to roll back away from the overlaying plate. Consequently, the overlaying plate is stretched. Tension and thinning may initiate seafloor spreading, enlarging the back arc basin. Okay, so here we have our subduction, okay, our volcanic arc being formed, okay, and this is going to cause slab motion. It's going to cause some pulling or the trench to roll back, causing this tensional force trying to stretch out this basin here, causing this back arc basin to form. Island arc type mountain building results from steady subduction of oceanic lithosphere. Continued growth can result in the formation of parallel mountainous topography, consists of igneous and metamorphic rocks. The Andean-Type mountain building, subduction beneath the continent rather than oceanic lithosphere, exemplified by the Andes Mountains, starts with passive continental margin, thick platform of shallow water sedimentary rocks. Eventually, the forces that drive the plate tectonics change direction and subduction zone forms. Oceanic lithosphere must be dense enough to sink. Okay, so here with the oceanic trench, it starts to subduct. Okay, and then we get some partial melting with nice accretion wedge, and then we have sort of all this volcanic activity that forms uplifting and forms these mountain ranges. Building volcanic arcs. As crustal rocks descend, water and volatiles are driven from the crustal rocks to the overlaying mantle wedge. These volatiles trigger the partial melting of ultramafic peridotite, generates mafic primary magmas which rise to the mantle wedge. Magmas pool at the base of the continental crust. Magmatic differentiation causes less dense magmas to rise through the crust. Emplacement of batholiths, a thick continental crust, impedes the descent of some of the magma. Most magma never reaches the surface and crystallizes underground as massive plutons called batholiths. Eventually, uplifting erosion exposes those batholiths. Examples like the Sierra Nevada in California, maybe some of the mountains in Georgia. Batholiths typically range from diorites to granites. Development of accretionary wedge. An accretionary wedge is accumulated sediments and scraped upper crust of the subducting plate plastered against the edge of the overriding plates, similar to soil and sediments being pushed by a bulldozer. Prolonged subduction may thicken an accretionary wedge enough that it protrudes above sea level. Forearc basin. The accretionary wedge acts as a barrier to sediment movement from the volcanic arch to the trench. The region of relatively undeformed layers of sediment and sedimentary rock is called a forearc basin. One of the Sierra Nevada coast ranges and Great Valley, one of the best examples of features associated with the Andean-Type subduction zone. Features produced by subducting of the Farallian plate, part of the Pacific Basin, are under western margin of California. So here, there's the mountains and landforms of the western United States. Here's that basin range region I keep mentioning when we have like the Horst and Graben terrain. There's the Colorado Plateau, Northern Rockies, the Columbian Plateau, the Sierra Nevada and Cascade Range, and the California coastal ranges. Cordilleran-type mountain building associated with the Pacific Ocean means unlikely to close. Highly likely that the subduction zones will form island arcs which will eventually collide with the continental crust. The collision and accretion of small slivers of continental crust form mountainous regions that rim the Pacific. Terrains or crustal fragments of exotic material make up much of the western United States. So here, collision and accretion of small crustal fragments to a continental margin. So here's the edge of our continent. We're subducting oceanic lithosphere. It's going to bring this inactive island arc close to our continent, and sliced off the subducting plate, and it gets smashed against the continent here. Okay, these island arcs forming these terrains. Okay, and then this new subduction zone forms. Here's the old one. So here's a new one forms, and then this microcontinent here then eventually collides and scrapes off against the continent and forms the next terrain. Nature terrains prior to accretion onto the continent. Some terrains were microcontinents similar to Madagascar. Other terrains were island arcs similar to Japan. Accretion and orogenesis. Small features on the ocean floor are subducted with the plate. Large buoyant features do not subduct. These features are peeled off the subducting plate and accreted onto the continental crust. Subduction continues on the other side of the crustal fragment. The North American Cordillera, many terrains that make up North American Cordillera were scattered through the eastern Pacific. During the breakup of Pangaea, the Farallian plate began to subduct under North America, resulting in a piecemeal addition of crustal fragments to the western side of North America. Terrains have been added to western North America during the past 200 million years. Let's see, area formed by accretion of terrains. This is blue area. And then these are all different colors of different terrains that have been accreted to the edge, western edge of North America. Alpine-type mountain building, continental collisions, a zone where two continents collide, is called a suture. Typically contains slivers of oceanic lithosphere. Most compressional mountains exhibit deformation of thick sequence of sedimentary rocks called fold and thrust belt. The Himalayas collision began about 50 million years ago. India collided with Asia following subduction of oceanic lithosphere. Precambrian rocks of India resisted deformation, while the younger crustal fragments of Southeast Asia were highly deformed. So here we have India traveling towards Eurasia, so the subducting oceanic lithosphere. Eventually, the ocean plate is completely subducted under. Some of it's been scraped up and mashed against the continent. This continental crust starts to push up this continental crust over here, forming the Tibetan Plateau and the Himalayas. Okay, so the Appalachians, of a similar origin to the mountains in the British Islands, Scandinavia, and Northwest Africa and Greenland, formed from three major orogenic events that accumulated with the formation of Pangaea. Tectonic or orogeny, the volcanic arc located east of North America was thrust over the continental block 450 million years ago. The volcanic rocks and marine sediment rocks were metamorphosed and exposed in New York. The Acadian orogeny, there's different parts of the building of the Appalachians, continued closing of the ocean basin resulted in a microcontinent colliding with North America 350 million years ago. Thrust faults, metamorphism, and granite intrusions are associated with this event, substantially added to the width of North America. The Allegheny orogeny, Africa collided with North America 250 to 300 million years ago. Material was displaced 250 kilometers inland on North America. Pangea then began rifting 180 million years ago. The rift was eastward of the suture, leaving a remnant of Africa welded to North America. Okay, so here's formation of the Appalachian Mountains. So here's North America, tectonic volcanic arc. And here's a subduction zone. North America, it collides with this tectonic volcanic arc, becomes a tectonic orogeny. And this subduction zone is bringing this ocean plate subducting under here, the Avalonia, and then this portion, this microcontinent, gets plastered onto the eastern edge of North America. Okay, and then the Acadian orogeny, this subduction zone. Now we have, so that's Avalonia has been plastered on, and then the Allegheny orogeny. Because final events is when Africa actually mashes against North America here. And then Africa starts, a rift valley starts to form, and Africa starts to detach from North America and starts creating the Atlantic Ocean. But here, so we have our coastal plain, the Piedmont region, Blue Ridge Mountains, the Valley and Range, and the Appalachian Plateau, which formed from all these different mountain building events. Continental rifting can produce upland, and continental rifting can produce uplift, and the formation of mountains known as fault block mountains. For example, the Tetons of Wyoming. Basin and Range Province, one of the largest regions of fault block mountains on Earth, located between the Sierra Nevada and the Rocky Mountains. Tilting of faulted structures called half-grabens have produced nearly parallel mountain ranges that average 80 kilometers in length. Extension began 20 million years ago as the stretch the crust twice the original width. Two different theories of formation. Following the subduction of the Farallon Plate, the northwest movement of Pacific Plate produced tensional forces that have stretched the region. 20 million years ago, the lower lithosphere mantle decoupled from the crust beneath the region. This delamination resulted in an upwelling and lateral spreading of hot mantle wrecks, producing tensional forces in the crust. Those are the two different ideas. So here's one model for the formation of the Basin of Range, on the Pacific Plate and the Farallon Plate. The Pacific Plate's kind of like pulling on the North American plate, causing a tensional force that's pulling on the rocks apart, causing those fault block mountains to form. Principal isostasy: less dense crust floats to the top of denser rocks of the mantle. Isostasy is a concept of floating crust and gravitational balance. Envision a series of different sized floating blocks in water. The thicker the block is, the deeper it's going to sink, and yet the higher it's going to rise as it displaces equal volume of water for the block itself. So a smaller block's not going to sink as far, and it's also not going to rise up as far. So as, let's say, this wood block was eroded, if this is a mountain, it would actually start, it wouldn't be sunk as deep, it would start rising, and that's how we have some uplift of our mountains. How is isostasy related to changes in elevation? If weight is added or removed from the crust, isostatic adjustment will take place as the crust subsides and rebounds. Crustal rebound is present in the Canadian Hudson Bay region following the melting of the ice sheets of that region. Because during the ice ages, the ice sheets actually added weight to our crust, so there was a lot of subsidence. But as the ice sheets have melted away, then the rock has readjusted and has uplifted. How high is too high? As mountains grow, gravity acts on the warm and weak rocks inside the mountains. Eventually, gravitational forces are so large that the rocks will flow laterally. This ductile spreading and consequential subsidence is called gravitational collapse. Okay, so here we've had so much uplift that we'll have gravitational collapse where the rocks are going to start then stretching out and thinning. Mantle convection, a cause for vertical crustal movement, uplift of whole continents. Mantle plumes can elevate a region on continental crust, for example, southern Africa. So crustal and also crustal subsidence. The slabs of oceanic lithosphere will detach from the trailing lithosphere. Downward flow is created as the detached slab continues to sink, pulling down the crust into a basin structure. So it's Michigan and Illinois area. That's the end of that chapter.